All right. Hi everyone. Thank you for the organizers for the opportunity to be here and first to be here to talk about a topic that is very near and dear to my heart, planets with two suns, and perhaps most importantly to go way outside my scientific comfort zone and try to look intelligent when I ask you stupid questions about Hagen Earth and prebiotic chemistry and early bombardment and all the amazing things that I'm sure you're going to hear about and learn over this week. I put my name here. I want to stress that the results that I will present are the product of a large team of people working together for actually many years, and it's been really a tremendous honor for me to be part of that team and to contribute to it. First, to make sure that we're on the same page, I would like to briefly describe what I mean by planet with two suns, using as an example this animation for a system is called QI 1338, it doesn't matter what's the name. But basically a planet with two suns is a planet orbiting a pair of stars. You see that there, it's kind of blurry, but I hope you see the two stars in the center. We have a so-called closed binary system, meaning that the orbital period of the binary star is typically 10 to 50 days. Outside of the orbit of the two stars, we have a planet orbiting both stars at the same time, orbiting around the center of mass of the system in a so-called circumbinary configuration. Circumbinary just goes around the binary system. So from the perspective of the planet sees basically two comparably bright stars at a comparable distance from the planet. I think planets with more than one sun, more than one, not just two, but more than one, have really long fascinated our collective human imagination. And I'm sure we all have our favorites amongst the fiction examples. I listed some that I'm aware of here. I'm sure there are many others. I really like this illustration from 1937 from Lucien Boudin. How do I know it's a planet with two suns? Well, there are two shadows behind the stones, two different colors. This is already telling us that the two stars are different colors. And the latest, actually, 2008, this is a three-body problem, which I'm reading right now, which I highly recommend. I also would like to spend one slide to introduce something that we've heard already, the so-called habitable zone. So I just want to briefly introduce the concept. Using as an example our very own solar system, the habitable zone is a concept that basically tells you how far away you have to be from the parent star so that the amount of energy you receive from that star allows liquid water on the surface. It does not guarantee liquid water on the surface, but the energy is enough to provide liquid water on the surface. And this is the incident stellar flux at the top of the atmosphere. So you can imagine it's very much dependent on what actually the planet is doing. So in the center here, you can see in the center of the center, the black dot, this is the sun. The blue circle, this is the orbit of the Earth, 1 astronomical unit away from the sun. The green donut, this is the habitable zone. The dark green, this is some nomenclature here. The dark green is called the conservative habitable zone, which is between runaway and maximum greenhouse. The light green is the optimistic habitable zone, between Venus and early Mars. Note that Earth is actually very close to the inner edge of the habitable zone, which I think is about 0.95 astronomical units. And I also want to stress that this green donut, it's not a donut, this green disk, it's practically constant, it's fixed in space and time on short time scales. Of course, as the sun evolves, this not donuts, this ring, this disk will. There was a word for this, annulus. I don't know the word. But you can imagine as long as the sun is constant, that green thing is fixed in time and in space. Now, this is very much in contrast to what the circumbinary habitable zone looks like. To demonstrate this, here you see the same thing, but for a circumbinary planet. This is the first discovered circumbinary planet on the main sequence binary star, Kepler 16 system. The nomenclature is the same as in the previous slide. The green is the habitable zone, conservative and optimistic in a differently shaded. The difference is now we have two stars in the center here, the two black circles rotating around the center of mass. Again, the blue is the orbit of the planet. The dashed black line, this is the so-called stability limit. This basically means that there are no stable orbits inside that limit. I also listed the parameters of the system on the right, the masses and the sizes of the two stars, the effective temperatures, the period of the binary star, and the period of the planet. Now, as you can see, this green annulus wobbles around the barycenter, the center of mass of the system, on the period of the binary star. This is very much different from what we have on single stars. Again, single stars, the annulus is fixed. Here, it wobbles every binary period. In this case, the binary period is 41 days. And if you look closely, the orbit of the planet goes in and out of the dark shaded green. This means that during a single year of the planet, it goes in and out of the conservative habitable zone multiple times. Now, because we have two stars in the center, there may be cases for a circumbinary planet where the orbit of the planet, where we have actually more than one planet in the system. To demonstrate this, here I've shown another circumbinary system. It's called Kepler-47. This is the first and so far only known multi-planet circumbinary system around the main sequence star. There are 3 planets in the system here. It is a little bit difficult to see the binary star here, but it's again, there's the 2 black circles in the center. The red is the stability limit. You can ignore this for the moment. And the 3 blue circles are the 3 orbits of the 3 planets around the binary system. On the right, I've shown the insulation at the orbits of planets C and D. So C is the outermost one, which you can see is in the darkly shaded green region, the entire orbit. And D, which is just skirting the inner edge of the lightly shaded green. On the right, I've shown the insulation of the orbits as a function of time for several binary periods, several planetary periods, and a few thousand days. The orbit of the outer planet is 303 days, the middle planet is 187 days. Now, as you can see, the insulation received by planet C, for example, it varies a lot for us in a single year. It varies by almost 20% in a single orbit. This is dramatically different from what single star planets do. On top of this, you have these crazy spikes down, which are the stellar eclipses. The 2 stars eclipse each other every 41 days from the perspective of the planet. So the planet sees the dramatic drop in the stellar light, which lasts for a couple of hours every 41 days or so. And here you can see the kind of longer term variability in the insulation. Despite the variations for planet C, it stays in the conservative habitable zone again for its entire orbit. The middle one, planet D, goes in and out of the optimistic habitable zone for about a third of its orbit. So it spends 2/3 in the optimistic and 1/3 outside the optimistic habitable zone. This is very particular for circumbinary planets because of this wobble. There's no animation here, I apologize for that, but hopefully you can imagine the wobble of the green annulus here. Now, because we have 2 stars in the center, there may be situations where a planet has a very long orbital period, yet still be in the habitable zone. Here is one example of this scenario. This is another Kepler circumbinary planet detected from the Kepler mission, Kepler 1647. The orbit of the planet is 1100 days, so this is nearly 4 years, but it is in the habitable zone for its entire orbit. This is because we have 2 stars that are a little bit more massive than the Sun in the center. You can again see the insulation of the orbit of the planet on the right. Again, you see the dramatic variations again on the order of 20% during a single year. So 1 year is 1,000 days. So 1 cycle, 2 cycles, altogether 4 cycles in general. Again, the planet sees the eclipses. You can see the impact on all of these effects on the habitability of the planet in general. And I also want to show 2 examples of circumbinary planets that are not in the habitable zone to highlight the dramatic variations in the received light from the parent stars, Kepler 34 and 35. I'll focus just on the one on top, Kepler 35, 34. I've listed the parameters of the systems here if you're interested. The black line is the incident stellar flux at the orbit of the planet, Kepler 34 in this case. Now you can see that in contrast to the previous two cases, here it varies not by 20%, it varies by 200% during a single year. This is a rather peculiar system. The binary star is quite eccentric in the center. The planet itself is also eccentric. All these parameters and calculations add up to make a very complex and very complicated habitable zone. Because we've already solved everything about single star planets, so we're looking into planets with a bit more than one star. My time is not working here, but I'll try to fill in. I want to mention yet another peculiar feature about specifically circumambient planets in terms of habitability considerations. This has to do with the rich dynamical environments of these systems. What do I mean by the rich dynamics? Because we have two very massive bodies in the center, and the planet is rather close to them. There are very strong interactions between the two planets, the two stars and the planet, to the point where, for some cases, like in this system here, Kepler 413, there is a very wide wobble, not at the habitable zone itself, which is always doing this, but the entire orbit of the planet is tumbling in space. This is shown in the upper panel here. This oscillation is real. This is what the planet is doing. This is how we see the planet, the orbital configuration of the system from the side. So in this case, the precession cycle, the precession period of the system is only 11 years. The precession cycle is how long does it take for this wobble to complete one period. 11 years is 10,000 times faster than what Earth does. Earth takes about 100,000 years to do one precession cycle. In addition, for systems like, for circumbinary systems like this, because of this flat misalignment, there may be so-called Cassini states. These are complex dynamical interactions between the angle of the orbit of the planet and the obliquity, the angle of the pole of the planet with respect to the plane. And there may be cases where you get to one-to-one resonances, sacral resonances between the orbital period and the obliquity precession period of the planet. What this means is that the obliquity, the axis of the planet, the angle of the axis of the planet with the general plane, can fluctuate by tens of degrees over tens of years. This is dramatically different from what Earth is doing, where it takes tens of thousands of years to wobble by a degree or so. So again, because you have two stars in the center, you're very close to two very massive bodies in the center that are constantly in orbit around each other. So with this, I would like to briefly wrap up the first part of my talk, depending on how much time I have for the second part. By the way, how much time I have left?
0.
0?
About 7 minutes.
7 minutes, thank you. So just want to summarize what I've mentioned so far. So circumbinary planets experience variable insulation or installation, whatever you want to call it, on multiple time scales. On the period of the binary star, on the period of the planet, on the precession period of the planet, on the precession period of the binary star, on the precession period of the obliquity. 1 in 3 of the known main sequence circumbinary planets are in the habitable zone. This is an astonishing fraction compared to single star planets. But there are caveats there, hopefully I'll get to those caveats. I also want to stress that all the known main sequence circumbinary planets are Neptune-sized and larger. We don't yet have a terrestrial planet around the main sequence binary star, but we're actually working on this, so hopefully in the next meeting I'll have better news for those who are interested in terrestrial planets. As I mentioned, the circumbinary habitable zone is not fixed. It wobbles on the period of the binary. It is close to the dynamical stability limit, which is important for the observations of these planets. Circumbinary systems experience these dramatic spin-orbit resonances on very short time scales compared to the Earth. And a very peculiar feature about closed binary systems, when I say close, again, tens of days orbital periods, is that tidal forces between the two stars suppress the magnetic dynamo mechanism and have the potential to dramatically reduce harmful effects for habitability. Namely, it dramatically reduces the chromospheric activity of the stars, the extreme ultraviolet radiation, and the stellar winds. To the point where maybe some of us say that they actually life may even thrive on some circumbinary planets because we have this dramatically reduced stellar activity, which is critical, especially at the beginning of the formation of the system. So for 5 minutes, I will try to very briefly walk you over how we go about discovering these circumbinary planets. It is very simple. We use transits. This is currently the only method to find and confirm main sequence circumbinary planets around close binary stars. Here you can see an animation of what a transiting circumbinary system looks like. We have two eclipsing binaries. We have an eclipsing binary star in the center. The two stars constantly continuously produce primary and secondary eclipses. You can see them in the brightness as a function of time function here. The plot at the bottom. Because the configuration of the system is basically agile from our perspective, the planet also produces transits across the two stars. So we see both the eclipses and the transits. Believe it or not, the only way to find these transits in the 21st century, when we have machine learning and neural networks and all this fancy magic, we do this by eye. We go to the photometry, we go to the light curves by eye, and for every available light curve of eclipsing binary. And we try to pick out additional features, additional to the stellar eclipses. Hopefully, I will have a few minutes to go through that, to go to the reason for that. Now, this is an animation, this is real data. I'm mostly an observer, so I want to show you what the data looks like. This is a section of the Kepler light curve of the first discovered main sequence of the Kepler 16. The upper panel shows you the flux as a function of time for over the course of a few hundred days. You see beautiful eclipses, blue, yellow, blue, yellow, the binary star in the center. You can see two of the eclipses here. Every now and then, every about 230 days, you have additional features highlighted in green and red. These are the transits of the planet across the primary and the secondary star spectrum. So we go through these by eye and we try to pick out these features. Why do we do this by eye, not by automatic algorithms? Well, they simply don't work. Because these transits, the circumbinary planet transits, they are neither periodic nor are fixed in shape. This is in complete contrast to what a single planet, to one planet is doing around one star, where the consecutive transits are basically identical. The timing, there is a little bit of a transit timing variation, but it's not dramatic. But the shape, the duration, and the depth of consecutive transits is effectively the same on human time scales. Circumbinary planets do this crazy wobble, that the orbit does this crazy wobble to the degree where consecutive transits, so this is parts of the Kepler light curve of one of the systems, Kepler 413. This is the same planet transiting the same star. Transit number 1, transit number 2, transit number 3, so on and so forth. You see how the transits dramatically change from one to the next. This is because everything in the system is moving. This is why we have to do this by eye, because traditional algorithms that rely on a periodic signal just fail. Because when you try to search for a periodic signal, all this is smeared out. And you do not build the signal to noise, so actually you lose signal to noise. Not only the transits vary in depth and duration, it's in some cases they completely stop. So there is data, the telescope is observing the target, there are no transits. This is effectively impossible on human time scales for single star planets. This is demonstrated here. I don't know if you can see the numbers, but transit number 3 is day 125. There is no detectable transit here. Transit number 4 is day 963. So there's 840 days gap between these two. The planet has a period of 66 days, but it did not produce any transits for 840 days because of this crazy wobble of the orbit. It just stopped transiting altogether. And it started transiting again after 800 days. And in fact, we could only detect this because of the long baseline provided by Kepler. Kepler had to observe this system for 1400 days. So it could pick out the first 3 and the last 5. So you can imagine that if we only had, let's say, a few hundred days of data, in the window where there were no transits, we would have no idea there's a planet there. This is a very typical feature for circumbinary planets. Here's another example, another Kepler discovery. 175-day planet, transiting, here transit number 123. 800 days of data, no transit whatsoever. Kepler observed the target, nothing happened. And then 1, 2, 3, different in shape, different in depth, different in timing. All again discovered by eye. How much time do I get left?
Wow. The official, 2 minutes.
2 minutes, okay.
So 1.5. So.
Alright, so I will just go all the way to the end. CDPs from Kepler and from TESS was one of the major breakthroughs from the missions. However, we only find a few, we only find a dozen or so. This is very similar to the state of exoplanets 25 years ago. In 1997, there were about a dozen or so known planets outside the solar systems. I shown them here in red. In terms of orbital eccentricity as a function of orbital period. I've also added the known transiting CDPs today. You see that there are literally 12 to 14 systems. So you can imagine that if we stopped observing for single stars in 1997, compare these dozen or so red points to the thousands of planets we know of today, and imagine what we would have missed if we just stopped observing in 97 and then said, oh, we know everything about it. So as exciting as the known CDPs today are, they're really just the tip of the iceberg, and they leave a very large gap in our understanding of what planets with two suns do. I will skip that. I would just like to hopefully pique your interest. What is next for CDPs? I think the future is bright, and we'll bring new exciting discoveries thanks to the observatories we already have, like TESS, James Webb, and Cheops, and to the future observatories that we'll hopefully be able to use in the near future, especially like Plato and W1st. Thanks to these observatories, I think we have for the first time the opportunity to tackle the still open questions of how do planets with two suns form, what is their characteristics, what is the population characteristics, how host binary stars form, and what is the population characteristics of the binary population that is hosting these planets. So if you're interested in planets with two suns, I would say stay tuned. There will be more exciting discoveries to come. Thank you.
Questions?
I don't know who raised first.
Thank you very much for the talk. It was very interesting. I don't know a lot about this, so I will definitely be asking a naive question. So if you have to pick this all up by eye and things are changing in terms of the duration, the shape, the depth, how do you determine the properties of these planets from their transits?
I'm so glad you asked this. You plug everything into a simulation. So you collect all the available data for a system. You collect all the available photometry, practice as a function of time. Not just from the observatory that you just used, but you go back into the archive, you see that the target was observed 10, 20 years ago from something else. You collect all the light curves available, practice as a function of time. You combine these photometric observations with all the available spectroscopic observations, because you need to nail down what the binary is doing itself. To do this, you need spectra. So you combine the photometry and the spectroscopy into this so-called photodynamical model, which is a fancy word for basically solving Newton's equations of motion. You put in the model the parameters of the system, sizes, orbital periods, masses, eccentricities, inclinations, like 50 parameters. You predict with the model where were all the bodies in the system at the observed times, because you know when an eclipse happened. For example, this is an example of an eclipse. You know that the day 1870 or whatever, 1878, there was an eclipse there. So you predict where the bodies are at the observed times. You use occultation geometry to see what was occulting what at that time. You just run the model, you minimize your residuals, and you produce something as beautiful as this. This is the fit of the model, so the data is in black, the black dots, and the model is in a black line. And then you basically solve everything about the system. This is a rather unique feature of multiply occulting multiple bodies. When you have more than two bodies occulting each other, you have a very good constraints on all the parameters in the system. That's why I said that this is the only way currently to confirm silicon binary planets, because the stars eclipse each other and the planet is also transiting them. When you have multiple bodies doing this, it's you basically solve the entire system.
Thank you.
Hi, thank you for the interesting talk. I have a question, maybe it's naive. I have several questions. The first one is, so here you may be talking about transiting planets. Is there anything that we can learn from real velocity, or is it just too complicated?
That's a very good question. The answer is yes, depending on the planet. So getting the binary is easy. These are the interaction velocities of the binary. Loud and clear, tens of kilometers per second is It's bang on. If the planet is massive enough and close enough, and you have long enough spectroscopic observations, you can try to actually detect the planet in radio velocities. This was done, I think, just a few years ago for the first time for one of the known systems. So we discovered the system from the photometry. People followed up the system from spectroscopy. They subtracted the binary radio velocities, and they pulled out the radio velocity from the planet itself.
Okay, thank you. And the second question, maybe a bit more far in the future. Let's imagine that we can do a transit spectroscopy with these planets. Why not? Can we learn about the fact that they are going to transit two different stars, and maybe it can help us constrain the atmosphere better than if it's just one star?
They do indeed transit both stars. This is one example. So this was tried. So the short answer that this was attempted for this particular system is the brightest known CPP. When I say brightest, it's like 11 magnitude, so it's not ideal. It was observed by HST. The only thing I know that there is no published result. The data is available. I don't know what happened. But people tried that system because it's the only available for HST in particular.
Okay, thank you.
As you pick for my talk tomorrow and during the week, maybe that I'm interested in small bodies in the solar system, and thinking about the formation of these systems and also the habitability of these systems. How much is known about the small bodies that might be there and the impacts that they might cause on the
Zero.
Any speculations from the orbital dynamics?
I mean, we are barely able to see the planets themselves. Barely able. When I go, after even smaller bodies. I mean, if you look at the signal here, it's coupling in terms of dynamical stability. Because currently, the way we design stability is basically run the antibody models for 10 million years. People try to do this to train neural networks to do this much faster, but that's the only thing that I know of.
I was referring to the characterization of the light curve, getting all the parameters with machine learning and photodynamic model. For example, if a machine can identify one transit and say, okay, well, I know the radius, I can get some prior, if this is, let's say, Jupiter-sized radius, probably the mass goes between 1 Jupiter and 10 Jupiter masses, and if I know the rest of the binary parameters, I can apply a photodynamic model and try to fit the light curve. That's fine.
Yeah, so I'll give you the cynical answer. The cynical answer is that people have successfully applied machine learning to detect already known systems. The computers still have yet to detect these before we do. So it probably is just a matter of time. But as you know, the systematics in the data are just horrible. So, and the human eye is extremely good at picking out systematics from these signals.
Okay, one last question.
I noticed that the size of the stars were dramatically different, and I'm wondering if the stellar output, the spectral frequency is very different, because it's a naive question as a biologist that would allow for two phases of a very different biological system and potentially different pigmentations on.
So you mean the sizes like the stellar radii?
Yeah, look from the animation, the stellar radii were very different, and I'm just wondering if the spectral output therefore is very different than both the intensity and the...
Absolutely, yes. Yes. So especially for systems where the stars are dramatically different, which is like this. So the primary star is like a K star, the second, and you can see what the difference is in the effective temperature in the two stars. So the second star is a tiny, faint M dwarf here, which is almost as big as the planet itself, the secondary star. So the output from that star is dramatically different from the primary star. Yeah.
All right. Thank you very much, Veselin, for a great talk. It is downstairs, so the recommendation is that you walk downstairs, eat as much as you can, and then walk up.